Our last little video in this section is going to consider something called racemic mixtures or racemates. Now when optical isomers are formed in nature, they're formed as only one of the isomers because the natural molecule has a stereospecific active site and just manages to form one. But if we try to make these in the laboratory, if we try to make these in a beaker, we will always generally form a 50-50 mixture of both enantiomers. So we'll just get both of the two mirror images in equal quantities, and when we get a mixture with equal quantities of each of these two enantiomers or optical isomers, we call it a racemic mixture. So how might you get this happening in the lab, and why do we get a racemic mixture? So let's consider a reaction that you should be relatively familiar with. Let's draw out butene. So but means that the double bond, but means 4 and 2ene means the double bond is on number 2. So I'm just going to draw it with its shape. I like to draw things with their shape. I've drawn the Z version. It doesn't matter whether you draw the E or the Z. I'm going to react it with hydrogen bromide. So if we remember back to alkenes, the hydrogen bromide molecule has to approach the alkene with the delta positive hydrogen closer to the double bond. If it doesn't, no reaction will occur. And our mechanism, we have a curly arrow from the double bond, of the carbon double bond attacking the electrophile, an electron pair acceptor. So the pair of electrons in the bond attacks the electrophile, and then the hydrogen Br bond breaks and the electrons are moved on to the bromine. What that leads to then is an intermediate, and this intermediate, we move these groups around, we'll put a hydrogen on here, and we've left ourselves with a carbocation intermediate. So this intermediate here is a carbocation, and we've got a bromide ion ready to attack. Now what you'll see is that the intermediate here has only got 3 bonds. Now although I've drawn those at 90 degrees, when a carbon has 3 bonds like that and no lone pairs, its shape is actually going to be trigonal planar. And because it's planar, the bromide ion can attack it from above or below the plane. So you can imagine, if you're looking at it on your piece of paper now, this bromide ion could come at it from on top, because it's flat on the page, or from underneath your page. Now if it came from on top, it would push the other atoms down back below the page that you're writing on, but if it came from underneath, it would push them forwards, and they are the two enantiomers. So I'm going to draw the rest of the mechanism, and then we'll write a little thing down to explain that. And this name of this mechanism, you should recall, is electrophilic addition. And if you've forgotten this mechanism, it's a good idea to pause the video now, go back to your alkenes notes and have another look at it and maybe practice it a few times. So let's just remind ourselves about the shape of the intermediate. Remember that the carbocation intermediate here is trigonal planar, and it's the part about it being planar that's the most important. So what we've got is the bromide ion, the Br minus, can attack equally from above or below the plane, leading to a racemic mixture. Got some final points to note here. A racemic mixture will not rotate plane polarized light. That's because each component does rotate it, but because they're in equal amounts, their effects cancel each other out. And then the other thing to bear in mind is that they do have, optical isomers do have the same chemical properties. So you can't distinguish them by a test. You can't test to see if it's one or other of the optical isomers with some chemicals, but you can look at the way they affect the plane polarized light. Now this comes up in exam questions all the time. So students end up changing correct answers to incorrect answers because they feel like they must have gone wrong. So the question may be phrased something like, why did the mixture not rotate plane polarized light? And students are tempted to say that the mixture is not chiral. When the mixture is chiral, it's just that it's a racemic mixture. So they change their answer and they make their structure now not contain a chiral carbon. This structure does contain a chiral carbon, this one here. But they would change their answer so that it won't have a chiral carbon, and in order to say that it won't rotate the light. Now this has a chiral carbon, but it doesn't rotate the light because it's got equal amounts of both enantiomers. So you just need to watch out for that little question. That's the end of this little video. You can try some more exam questions on this. Find some from your exam board and have a go.